This is section 1.2. It's a video about truth tables, and to make this harder for myself, I'm going to try and fill in the truth tables live in the video. Let's see how that goes. So the idea for this is it's a way to systematically work through different cases, to go through the cases of whether or not statements are true or false. So here, I'm thinking about statements like we saw in the previous video, where maybe X is in A, and that might be true, or it might be false, depending on, I suppose, what the set A is, and depending on the element X. I'm going to write T and F for those cases. Similarly, we might be thinking about a different subset B, and again, it might be true or false, whether or not we're in, our element is in the subset B. So we have a bit of a shorthand here. Along the top, I've got different subsets of S, and in the different rows, I'm looking at the different cases for whether or not it's true or false that an element is in each of those subsets. So, for example, this column A, I'm thinking about the statement, is X an element of A? And I'm working through cases where it might be false or true. And in this column might B, I'm thinking about cases where the element might be in B or not. So that's my setup, where I've got subsets A and B, and I've just gone through all 4 possible cases. If I had a third set, C, there would be 8 cases to think about, 8 rows in this table underneath. I'm not counting the header row, that's row 0. And there'll be 8 other rows of the table with all of the different combinations of F and T. And this gives you a systematic way to think. It's not quite for each element of S, but it does track all of the possibilities relative to membership of A and B if you have a more complicated statement that you want to investigate. Because all of these more complicated statements are just things to do with whether or not you're an element of A or B. So although the set might be infinitely large, there's only finitely many cases that we care about. I don't care which element of A we're talking about. For our purposes right now, we only care about membership. So for example, I've got a double line here because these are sort of my inputs of all the possible cases. They define the rows of the table. And then I can think about concepts like the intersection, the idea of being in A and B. And that works like this, that if your elements are in neither A and B, then I don't want that. I don't even want this. Intersection says you have to be in both. So I draw this column, which you could say is the definition of intersection. It's true that you're in the intersection precisely if it's true that you're in B and true that you're in A. So maybe I should have shown you a truth table for the definition of A intersect B. Not sure you would have liked it, but I'm not sure I like it. But here's the kind of different cases in each column. We could also look at A union B. So this one is permissive. You could be in one or the other, and we said or both. It's not that permissive though. You have to be in one or the other. So F T T T for this case. And just as an example, the set difference A but not B, we have so that is the case if you are in A but not B, so it's this one, and then if you're in A and B, that's precisely the ones I'm trying to remove. So you might be in A, but no set difference says you're in B, I don't want that. And then the ones that are not in A, I don't want those either. So if you like, this is a definition of the set difference A minus B, where in my head I thought about diagrams and I thought about inclusion and membership and being removed. But there's an alternative which maybe you remember. We defined this thing, we also said that it's equal to A and not B. So A intersects the complement of, this. A intersects the complement of B. You have to be in A and not in B. And that's a sort of compound statement with different parts to it. You can build this up So my examples here, I was reading my input columns and thinking about whether I was in this or not, but we could build something more complicated by using these columns and thinking about, I don't know, the union of these two columns by just reading across. So union always means you have to have at least one T. You have to be in one or the other. I thought we could use this for an example. Quickly, let's check. I have a slide which has the answer on, so if this disagrees with the previous slide, then you're not going to see this because I'm going to start the video again. 2 T's, a T in the middle. Oh, I got it exactly right, good. Okay, 2 T's over there. Yep, I'm good. Okay, I'll stop flipping between the slides and move on to a proof of De Morgan's law, which has lots of columns because I need to calculate these complicated compound things. But then the idea is that we can just compare columns. If you match in all of these cases, then you're the same subset because you have the same cases. Elements might be in A or B or both or neither. Those are all of the cases. And these things are all built just by looking at membership of A and B. Which means that because those things I'm going to write in the columns might be T or F, there's only actually 2 times 2 times 2 times 2, 16 possibilities for the column. So maybe it's not surprising that some statements turn out to be equal because there's only 16 things I can put in a column. Maybe your set is infinitely large, but for my purposes, intersections and unions and complements and things can only give me 16 different looks. Right, we had some of these before. So A intersect B, I had on the previous slide. That one says you have to be in both. Exactly both like that. A union B, that was a bit more permissive, these. And this table, I'm also going to need to talk about A complement and B complement. So these ones are a bit funny. The first one there doesn't depend on B at all. So it just goes true, true, false, false. So if you're not in A, then you are in A complement, and vice versa. And this column is sort of independent of B, but whatever. Okay, I've got to concentrate on B complement because that one goes like this. Okay, so then what I want to show is that we can build more complicated things. Let's start with these complements which appear in De Morgan's laws. So this is the complement of this thing in the previous column. So I can look at this column and calculate the complement. And if you like, this complement thing just says the opposite. So this F here turns into T here if you're not in the intersection. So in this case, whatever the case is, I'm no longer looking over here at all. Whatever this case is, my element is not in the intersection, so it is in the complement. So I get this. Okay, so it just switches these, going from there to there. And similarly, over here, if you're playing along at home, you can fill in a copy of this table. But I haven't given you any notice to create the table, so you'd have to be very, very quick there. Do complements of all of those things. Okay, so we've got true, 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 false, and we've got true, false, false, false for those complements. And then over here, I've got things which look at the union of some complements. So now it's a bit like starting a new truth table to the right of this line, I suppose, where I have A complement and B complement, and then those are the things that I'm working with. So the cases are in a different order now, I suppose, compared to what I was doing over here. But it's the same sort of thing, right? I have the union of these two things, and the union of these two things means you have to be in one or the other. If you like computer science and logic gates, you can maybe think about what we're doing here as an operation on inputs and outputs with binary inputs, true or false, 1 or 0, and binary outputs. Okay, and then intersection at the end really says you have to be in both, so it's T at the top, and then false, false, false down here. Where I'm just looking at these columns and thinking, TT, my rows appear to have been scrambled or something, but whatever. I'll go TFFF. So you have to be true in both columns. That might be impossible, I suppose. It's not always the case that picking any two random columns, you see that characteristic combination of F's and T's. I mean, over here, if I pick these two columns, then I think these things are opposites, so I don't go through all four possible cases. But sometimes it is true that you look at the inputs and you have all possible inputs. In which case you can think of it as being a permutation of the rows. They've been scrambled around. Anyway, the punchline here, in a different colour, the punchline is that the complement of A and B is the same as A complement union B complement. That these columns are exactly the same as each other, which is good news. It means in every case, no matter which subsets you are a member of over here, it's always going to be in any of those cases, either you're in this highlighted set or not, exactly when you're in this highlighted set or not. And similarly, for the other De Morgan law, we can look at A union B complement, and we can look at A complement intersect B complement, true, false, or false. So I've done a lot of talking there, but hopefully you can see how you build this cumulatively, to start with a comprehensive list of all of the cases, and then to try and build more complicated things out of those, so that you can say at the end that I've looked at all of the cases down the left for A and B, and in all the cases these two sets agree, which once again, you might be surprised how often that happens, because there's not very many ways of filling in a column with T's and F's. Okay, that's truth tables. You're welcome to use them if you like, if you want to systematically work through cases. Okay, in the next video, we're going to have a look at cardinality, which is a measure of the size of a set. So I'll see you back for that one.